this week's episode of Climate Wise. My name is Sam, this is Lauren, and we will be your hosts guiding you through tonight's piece of scientific literature.
That's right, Sam. If you are a busy individual looking for up-to-date climate science condensed into 6 minutes, then you've come to the right place.
So let's get started. Today's paper is Limited Contribution of Permafrost Carbon to Methane Release from Thawing Peatlands by Cooper et al.
So let's break this down, Sam. I know about carbon dioxide and how it can contribute to climate change, but I know less about methane. What is methane and why do we care?
Good question, Lauren. Let's have a look, shall we? Methane is a molecule composed of 1 carbon and 4 hydrogen molecules. It is a greenhouse gas like carbon dioxide, which essentially means that it stays in the Earth's atmosphere and absorbs the sun's reflected long-wave radiation, keeping the planet at a livable temperature. However, recent anthropogenic carbon emissions have caused a major increase in the atmospheric concentrations of greenhouse gases such as methane, and have begun altering the Earth's climate. Methane is particularly concerning since it is a far more potent greenhouse gas than carbon dioxide. So where does methane come from? Methane can come from a variety of natural and anthropogenic sources. Examples of anthropogenic sources include livestock and agricultural practices, the production, transportation, and refinement of fossil fuels such as coal, oil, and natural gas. Natural sources of methane include the ocean, as well as environments that contain high amounts of organic carbon that can be broken down to create methane, such as wetlands and peatlands. In this video, we are going to focus on the last source and how current science is shaping our understanding of the underlying mechanisms of these methane emissions.
That's great, Sam. So first things first, what are peatlands, where can I find them, and how do they release methane?
Well, Lauren, for this discussion, we are going to have to go to a little northern country known as Canada! Specifically northern Canada, in Yellowknife Northwest Territories and Teslin, Yukon. So why Canada, you may ask? This is because Canada hosts a large area of peatlands, but not just any kind of peatland, permafrost peatlands. Peatlands are landscapes consisting of a mixture of plant organic material that have accumulated as a result of a lack of oxygen plus an abundance of water, which are conditions that promote slow decomposition rates. This means that what you see behind me is essentially a big pile of carbon. In northern latitudes, peatlands contain a layer of permafrost, or permanently frozen ground, that can ultimately play a huge role in the decomposition of this organic material. Permafrost melts, such as in times of increased temperature. Carbon that was previously frozen becomes susceptible to decomposition. The decomposition of carbon in oxygen-deficient waterlogged environments such as peatlands thus have potential to produce methane in a reaction via microorganisms known as methanogenesis. Therefore, thawing permafrost can cause peatlands to go from storing carbon to emitting it into the atmosphere in the form of methane, thus causing a positive feedback mechanism. With a positive feedback mechanism, the output enhances the original stimulus. In the specific case of permafrost carbon feedback, as global temperatures rise, more permafrost is thawed, which causes more carbon to be exposed to decomposition, thus releasing more methane into the atmosphere and raising global temperatures, thus repeating the whole cycle. However, Cooper et al. Proposed the idea that melting permafrost could be emitting methane through a different mechanism. When permafrost is present in peatlands, it pushes the peat up, creating what is called a peat plateau, which is removed from the water table and can host a variety of terrestrial species such as trees, shrubs, and moss. These areas experience very little methanogenesis. In contrast, when the layer melts, the ground below it subsides, causing the peat to fall below the water table. The saturation of these organic soils allow aquatic plants to thrive and promotes the release of methane.
Very interesting, Sam. So what you're saying is that Cooper et al. Looked to quantify how much methane is actually emitted from the previously frozen carbon and to see if emissions could more likely be attributed to changes in subsidence and waterlogged area.
Yes, Lauren, that's correct. Cooper et al. Chose to investigate this idea using radiocarbon dating. Radiocarbon dating involves the use of isotopes, which are elements that have a different number of neutrons. Carbon has 3 main isotopes: carbon-14, carbon-12, and carbon-13. Carbon-14 is radioactive, meaning it decays over time, which is why it is useful in dating methods. In this study, the more recent input of carbon into the peatland has a higher carbon-14 content than older, previously frozen carbon. This is reflective of the large input of carbon-14 into the atmosphere during the 20th century when there was extensive nuclear testing. So in this study, these scientists put probes into the soil at 2 different sites mentioned in the locations in northern Canada, ensuring to get samples from both peat plateaus and subsided peat at each site. This allowed Cooper et al. To assess 2 different pieces of data. Number 1, the carbon-14 content in each section of the peatland. Number 2, the carbon-14 content in the methane released from each section. They looked at these two sets of data in order to link the carbon-14 concentration found in the peat with the carbon-14 content found in the methane being released at each site. This is what they found. The overall permafrost zones that had substantial methane fluxes were dominated by the decomposition of recent carbon inputs. The total methane released from previously frozen carbon were very low. This low rate of methane released may be due to the fact that under long-term anaerobic conditions, compounds known as phenolics build up and repress microbial activity in the older, deeper peat layers. The methane fluxes did seem to be linked to surface subsidence, as the Teslin site had higher methane emissions and a larger area of subsided peat and waterlogged soil. Overall, it can be said that subsidence and waterlogging of recent carbon stocks plays a bigger role in the permafrost carbon feedback than the exposure of previously frozen carbon stocks to decomposition.
That's all very interesting, Sam. But why do we care?
Well, Lauren, currently a number of climate models predict that anaerobic decomposition of previously frozen peat will predominantly impact climate feedbacks. However, this is obviously not the case. Therefore, it is important that permafrost feedback modeling with respect to the northern Canadian peatlands be focused on the spatial extent of waterlogged areas and subsidence, in order to make more accurate predictions for the future.
Well, Sam, I think that's all for this week's paper. Thanks to all you folks for tuning in on this episode of Climate Live, and we hope to see you again next time.